Hello, ladies and gentlemen. Welcome to the lesson on heating and insulating buildings. This lesson fits with GCSE Physics and also combined science in the first physics topic about energy transfers. And we've been talking in the last few lessons about thermal energy transfer. So this really brings those ideas together. So today we're learning about how we can control the rate of thermal energy transfer using insulators and conductors and why this is important. And specifically, we're going to be looking at insulating buildings in that context. So the do now is about conduction, convection, and radiation. There's a diagram just there that shows all three of those processes occurring at once when we're heating water in a pan on maybe a hob. What I would like you to do is to write a sentence that describes how each process, conduction, convection, and radiation, how each process transfers thermal energy. And what you will need to do is you'll need to include ideas about moving or vibrating particles and the emission of electromagnetic radiation. It would be a good idea for you to pause the presentation at this point for a few minutes and write down some sentences now. Okay. So let's have a talk about how we might describe each of these processes. So the first one, conduction. Conduction is the thermal energy transfer through solids, particularly metals, by the vibration of the particles in the fixed lattice and the movement of delocalized electrons in metals. So let's break that down and let's think about the important parts of that model description. So the first thing, conduction is, it happens through solids and especially metals. And that is because those solids have particles that are close together. So when they gain energy, they vibrate, and those vibrations, because they're in a fixed lattice, get passed through the material. And that will gradually progress through that material. But in a metal, it will happen much more quickly because it also has delocalized electrons that can transfer the energy very efficiently. So conduction occurs through solids, especially metals. So anything that's not a metal is a poor conductor, and things that aren't even solid are very poor conductors. So water and gases really don't conduct at all. Convection is thermal energy transfer through liquids and gases, and the word fluid means a liquid or a gas, something that can flow. Convection is thermal energy transfer through fluids due to the expansion of the hotter parts of the fluid, causing the fluid to be less dense, so the particles rise. And then the contraction of the cooler parts of the fluid, which will cause the fluid to become more dense, and so the particles sink. So if you look at the diagram of the pan there, you can see that the fluid particles at the bottom, the liquid particles at the bottom, are reasonably closely packed. But then as they gain energy, they vibrate more, they move more, and therefore they move apart. The material expands. That means it's less dense, and so those particles rise up. The particles at the top are then less dense, but they're away from the heat, so they lose energy and they start to vibrate less, so they come together. They become more dense, and so those particles sink. And what you can see is a convection current that rises up and then falls down again. And it's this cycle we call a convection current, and it happens only in liquids and gases. So conduction happens through solids, particularly metals. Convection happens in liquids and gases. Radiation, you should know this if you've watched the previous lessons, is thermal energy transferred by infrared electromagnetic waves. So infrared radiation, and you can see that infrared radiation being radiated from the hob just there. All right, so our learning outcomes. You can see that we hopefully can be able, by the end of the lesson, be able to describe the three different ways that thermal energy can be transferred. Hopefully we can already do that. We'll be able to explain the different ways that insulators reduce the rate of thermal energy transfer, and also then apply those ideas about insulators and conductors to explain how they can be used together to heat or insulate buildings efficiently. So really this lesson brings together those ideas about thermal energy transfer and then applies them in specific situations. The final couple of slides in the lesson is about payback time, which is a higher tier idea where it'll involve you making some calculations, and I'm going to show you how to do that, to talk about whether a particular method of insulation is cost effective or not. Okay, so the first thing we have to do when we're talking about heating and insulating buildings is to understand what makes a good insulator. So there's a couple of video clips that I'm going to show you here, very short ones. I'm going to play those now, and I'd like you to concentrate on particularly why certain materials might not be good conductors or convectors.
Cooking pans and baking tins are usually made from metal, typically iron, steel, stainless steel, copper or aluminium. When we heat a metal pan on the hob, or a baking tin in the oven, it quickly heats up and transfers heat energy to the food inside the pan. It does this by the process of conduction. Metal is a very good conductor of heat. This is because of its atomic structure. The atoms that make up metals are tightly packed together in a lattice. As the heat energy from the hob is transferred into the pan, it makes the metal atoms start to vibrate. As they vibrate, they pass on the heat energy to other atoms nearby, and they pass it on to others, and so on. This is why, if you put a metal spoon into a pan of boiling water, it will gradually heat up until it is too hot for you to hold. Metals are very good and efficient conductors of heat compared to other materials, such as ceramics and glass. It's important for a pan to have a well-made, flat and strong base so that it stays in close contact with the hob and allows the heat energy to conduct through it evenly. Poor quality pans may warp because their base is too thin, which means that heat will not be transferred evenly. Some materials, such as wood, some plastics and thick materials such as cotton and wool, are poor conductors of heat. They are called heat insulators and are used in a variety of ways to prevent us from burning ourselves when we're cooking. For example, pan handles are often made of plastic or wood so that they're comfortable to hold. Some pans have metal handles which are hollow inside, so the air they contain prevents the metal from becoming too hot, as air is a heat insulator. Whatever material the handle is made from, it's important to remember to position pan handles away from the direct heat from the hob. Subject to heat like this, any material will eventually become too hot to hold.
Okay, so the important thing there, it showed you a diagram that showed the vibration of the metal particles conducting very well. The key thing for conduction is about the particles being close together, as we've already said. So what makes a good insulator? Oops, pause that. The key thing is that gases are poor conductors because their particles are widely spaced. So the vibrations are not passed through material. So gases are good insulators. When the particles are widely spaced, they will not conduct well. Therefore, it is an insulator. Okay, so the next part of this is a short video that shows or demonstrates convection, and you can do this at home. I'll just pause it there for a second. It's just a tea bag that you can see there, standard tea bag, one of the string tea bags. Now, if you snip the top off the tea bag, what you'll find is that it forms a cylinder of the material that's the bag. You get rid of the tea inside, you don't need that, but you get a cylinder that you can stand on a non-flammable surface, so like a baking tray or something like that, well, watch what happens. You light it at the top, burns down. But when it gets to the very bottom there, drifts up into the air and then slowly sinks back down again. So why does that occur? Well, this is clearly something that shows the convection current caused by that heat. So we're going to stop that. So convection occurs, just move myself over here. Convection occurs when fluids can circulate in a convection current. So the key thing here is this: we've just said that gases are very poor conductors, but gases are very good convectors. So the problem is this, is that if you have a good insulator, what you want is something that won't conduct, but also won't convect. So small air gaps prevent convection. So if you've got a small space or you've got trapped air pockets, that will prevent convection. So a good insulator will be something with trapped air pockets and that is also a poor conductor. And you've got that typical diagram that shows convection on the right hand side there, where the warm air rises and the cool air sinks, as we've already discussed. Now, putting that together, what makes a good insulator? Well, A material with small air gaps and a low thermal conductivity will reduce energy loss by conduction and convection. So you can see there some typical loft insulation material. It can be made from a whole range of different things, but in many cases mineral wool or fiberglass is often used. And if you have a look at this, you can see, if you look at this carefully, you can see that there are lots and lots and lots of fibers with tiny little air spaces in there. So this would be an extremely good insulator because it reduces energy loss by conduction and convection. So several typical uses of conduction and convection. If you think about a mountain jacket, it's got hollow fibers inside, very much like the wadding you can see in the loft insulation. You've filled the jacket with that, and so that makes that a very insulating jacket because it's full of small pockets of air that are trapped. Another more natural use, really based on the thermal jacket is based on this, but you've got animals like these snow monkeys with really thick fluffy fur, and the whole idea of thick fluffy fur is that it traps small pockets of air. So again, reducing energy loss by conduction and convection. But the other thing is this, is that heat can also transfer by radiation. So that insulating materials often have silvered surfaces, and these reflect infrared radiation. They don't emit or absorb infrared radiation. So very often you would get the insulating material and you would have a shiny surface on one or both sides, so that we're not only stopping conduction and convection, but we're also stopping radiation. The picture that you can just see there is in fact expanded aluminium. It's aluminium that's had high pressure air forced into the material to create these little pockets of air. So that makes a really good insulator. What you could also do is get things like expanded polystyrene and put foil on the inside of it, and that would have the same effect. So you've got the silver surface and then you've got the small pockets of air, very good insulators. So let's reflect on our learning outcomes. Hopefully now we can describe these three processes, conduction, convection and radiation, and explain the ways that different insulators can reduce the rate of thermal energy transfer. If you haven't understood that, or if you need to go over it again, that's absolutely fine. But I've put a URL there for BBC Bite Size, and there's about 5 pages on the Bite Size website for this that go through conduction, convection and radiation very clearly, and also shows the way that different insulators work. So I would recommend that you have a look at that if there's any aspect that you didn't quite understand. Right, so now we're starting to apply how we use insulating materials and how we can prevent thermal energy transfer. So you've got a little model of a house, you've got 5 different ways that the energy can be lost, and I'd really like you to spend a little bit of time thinking hard, discussing with anybody who's near you, but how could you insulate the house to reduce the amount of energy lost from those 5 different areas? And the challenge aspect of this is then to describe how each insulation method you describe reduces the rate of thermal energy transfer. So we're talking about how they reduce conduction, convection and radiation specifically. So it would be a really good idea for you to pause the presentation now and have a think about that, maybe make some notes. Okay, so thinking about these different ways, clearly the first thing is this: if you're going to deal with the roof, the heat loss in the roof, you put loft insulation. There's 2 different images of loft insulation there, and in fact you can see the guy with the silvered. You've got the expanded foam insulation with silver foil on both sides, which makes that pretty efficient in the loft space. Also very lightweight, and you've got that guy handling the mineral wool. The windows, clearly double glazing is the key. And actually you've got some notes on there. Double glazing basically has 2 panes of glass, and in the middle of there you've got either a vacuum or an inert gas like argon filling that space. And some double glazing also has a low E² coating. That's just the name of a very fine silvered finish that you put onto the windows, often using nanotechnology. And that will allow visible light through, but not infrared radiation. So infrared radiation is reflected back into the house, or on hot sunny days, infrared radiation is reflected back out to prevent the house getting too warm or too cold. Drafts, pretty obvious and low tech. Draft excluders. You may see, if you've got drafty doors, you may have those sort of brushes attached around the door jamb, or one of those cute little sausage dogs or something like that. Floors, pretty obvious. You can put insulation very similar to what's been placed in the loft underneath the floorboards, but actually a good carpet and underlay is a really good way to insulate from heat loss through the floor. And finally, the walls, we often use wall cavity insulation. So different ways that we can insulate a building and prevent energy loss. But the challenge aspect asked us, how does each method reduce the rate of thermal energy transfer? So in terms of this, there's really two main types. You've got standard insulation, and we've got double glazing, which is slightly different there. So in each case, and here's the key words here, the insulating materials contain small air pockets. So where you're talking about an insulating material, you're looking for an air pocket or an air gap that's trapped, it can't move. So air is a poor conductor, and because it's trapped, the pockets cannot convect. Those are the key aspects of any insulating material. Double glazing has a vacuum gap that we just spoke about, which prevents conduction and convection. A vacuum gap is even better than an air pocket because there are no particles at all. So conduction cannot happen, and because there are no particles, convection can't happen either. But when you have a vacuum gap, sometimes the seal breaks and the double glazing doesn't work anymore. So in that case, they sometimes pressurize it with an argon fill, which is also a very, very poor conductor and convector. Now, as we've just mentioned earlier, some materials and double glazing have silvered surfaces, and the key idea of silvered surfaces, it reflects infrared radiation back into the building, in this case, and it does not emit infrared radiation. So we've spoken about emission and absorption in the previous lesson. Silvered materials are very poor emitters and absorbers. So one side will reflect radiation back, so it stays warm. The other side will not emit, which also then prevents the heat transfer out of the building if it does get through. So let's have a look at this. Hopefully, having thought about that, we can apply ideas about insulators and conductors to explain how they're used together to heat and insulate buildings efficiently. The key words that I've underlined there in terms of conduction and convection, small trapped air pockets, and also silvered surfaces reflecting and not emitting radiation is very useful. There's a short video clip, a Free Science Lessons video clip that really goes through that in detail if you want further clarification or that to be explained in a slightly different way. So now let's look at you applying some of these ideas. Now, there are 3 questions that we're going to go through. We're going to do some purple pen work on this, but this will work best if you download from Google Classroom the question sheets and make some notes so that when we go through the ideal solutions, you can build upon that. That will really help you to embed your learning for this. But the first one we're going to talk about is a vacuum flask. And this is a quality of written communication question. You will get 1 or 2 of these in every single exam you do for science. And so it's a 6-mark question. So you need to use good English. You need to organize your ideas clearly and use specialist vocabulary in terms where appropriate. That means that you can write your answer in bullet points, and that's something that we recommend. What we've got here is a diagram showing the structure of a vacuum flask, so a typical thermos flask, for example. The vacuum flask is designed to reduce the rate of energy transfer by heating processes. Describe how the design of a vacuum flask keeps the liquid inside hot. So you have hot liquid inside this flask, and it keeps that liquid hot. So what I would like you to do is make sure that you've downloaded the question sheet, stick it into your notes, however you're recording those these days, and then write down your answers, and we'll look at it shortly. Pause the presentation now. Okay, so in this question, to achieve the full marks, you will need to write a detailed description of at least 2 features of this vacuum flask. And there are 3 main components here that we could choose from, but you need to make a detailed description of at least 2 of those features to get full marks, to be sure of the full marks. So the first thing that we're going to look at is the plastic cap. If you look at the plastic cap and lid, you've got the fact that plastic is an insulator or a poor conductor. So that basic statement saying that the plastic cap is an insulator gains you a mark. Then detailed description of, sorry, we're not going to look at the detailed description just now. The other features there are a double-walled glass container and a vacuum. So you can see there we've got a vacuum between a double-walled glass container. That's why thermos flasks are so delicate. If you drop them and the glass container breaks, then obviously it doesn't work nearly so well. But glass is an insulator, and a vacuum, as we've just discussed, is also an insulator because it doesn't conduct and there's no convection going across that gap. The last feature is silvered surfaces. So you have silvered surfaces on the insides and outsides of that glass container. And if you look inside a thermos flask of some sort, you will see that they do look silvery. And the reason is they reduce, silvered surfaces reduce thermal energy transfer by radiation. So 3 basic statements. If you've just identified those 3, you'll get 3 marks. Now, the detailed descriptions are where the rest of the marks come from. So the first thing is there. So a plastic cap prevents conduction and convection of heat through the top of the flask because plastic is an insulator. It will also, and here's the extra mark for this one, it also prevents evaporation. If you didn't have that stopper, the hot liquid would evaporate. You'd see steam rising off the top, and that's another way for it to lose energy, lose thermal energy. So it prevents evaporation of the more energetic particles, leaving whatever's behind less energetic. How does the glass container and the vacuum work? Well, it reduces conduction through the walls of the flask, and the vacuum specifically prevents conduction and convection because both of these processes need particles. So here, to get the full marks for this description, we need to talk about particles and how conduction would apply or not in this case. The silvered surfaces, we know it's about radiation. Well, what's going on? Well, the silvered surfaces reflect infrared radiation or heat back into the hot liquid, and they are also poor emitters and absorbers of heat, so they won't be emitting on the other side either. So poor emitters and absorbers, but also good reflectors, and that's the way that we get the maximum marks for this. Right, the next question that you can download and print. What we have here is a diagram showing a solar water heater. Cool water circulates in through a pump, gets pumped through a pipe on the front of the solar panel. The sun rays hit that solar panel, and then you get that hot water out that you can store in a water tank and use for later on. And this is something that is used very often in poor countries where there's no access to hot water or electricity very often. So a good way to get hot water. So the questions here, you need to complete the 4 questions based on this. So again, make sure you've downloaded and printed this sheet and stuck it into your notes. And I'd like you to pause the presentation and have a go at answering those questions. 7 marks in total available for this. Right. So completing the sentences. So the following sentence. So heat energy is transferred from the sun to the solar panel by radiation, or infrared radiation is the answer. So the sun's energy is transferred to the earth and to the surface of the earth by radiation. Question 2. The pipe inside the solar panel is painted black. Why? Well, hopefully we understand, particularly if we've paid attention to the last lesson, that black surfaces are good absorbers of infrared radiation. So when the sun's radiation hits the pipe, because they are black, they will absorb that heat energy very easily. So the pipe will get hotter and transfer more of that thermal energy to the water. Okay, so that energy gets into the water more quickly because that's what we want here. Right, there's a layer of expanded polystyrene behind the black pipe. Why? Well, expanded polystyrene is a good insulator because it contains lots of trapped pockets of air. So the thermal energy will not conduct or convect easily, and so the pipes stay hotter. So when the pipes get hot, they stay hot. So we're insulating it so that those pipes don't re-radiate that energy back into the back of the heater and into the atmosphere behind it. So, so this is really important. How do we get the 2 marks here? Well, we say that it's an insulator, and then we describe why it's an insulator and why that's important. Finally, a silvered surface is used at the back of the panel. Explain why. So the silvered surfaces are good reflectors and poor emitters. So as we said for the thermal flask, silvered surface, good reflector, poor emitter. So any thermal energy that manages to escape through the back of the pipes and through the expanded polystyrene will then be reflected back. And if it does get to the edge of the polystyrene, it won't be emitted because silvered surfaces are very poor emitters. And hopefully you can see a pattern here. We're talking about the way that we prevent conduction, convection, and radiation, or in some contexts, how we promote it. So the blackened pipe is a way of promoting that transfer of heat energy, whereas the silvered surface in the polystyrene is a way of slowing it down. And that can be used in a whole range of different ways. Right, so hopefully now we can efficiently describe the 3 ways that thermal energy can be transferred. Hopefully we can explain the different ways that insulators can reduce the rate of thermal energy transfer, and hopefully we can apply those ideas to insulators and conductors and explain how they can be used to heat and insulate buildings efficiently. Excuse me. And we've just had the 2 example questions that show us how we might insulate something like a thermos flask, which is the same as a house in terms of preventing heat transfer, or how we could actually use heat transfer to capture that heat. The final thing that we need to do is look at payback time for a range of different energy saving and insulation options. So here's a question for us to have a look at. So homeowners often try to improve the energy efficiency of their houses to save money on energy bills. One way to improve the efficiency is to add loft insulation. The table below shows some information about the different types of roofing and loft insulation, and there are a series of questions there. Excuse me. So what I would like you to do is download the question sheet if you haven't done so already. Stick it into your book and then put your have a think about the answers just there, and we'll go through some work solutions in a moment. But now is a good time to pause the presentation and actually have a go for yourself. Okay. Now, before we continue, there's a term here, U value, that you may not have heard before. Now, this word U value may be important, and really all it means is it's a measure of the thermal conductivity of a material or an insulator. So the higher the U value, the more easily it conducts thermal energy. The lower the U value, the less easily it transfers it transfers thermal conductivity, thermal energy. So what we're really looking for is a low U value. So in this situation, homeowners are, so what we're doing, we're trying to, which type of roofing or loft insulation is the most energy efficient? Give a reason for the answer. So I'll pop that just down there. Okay, so the most efficient one is the one that's going to save the most energy. So if you look at this, the most energy efficient is the thatched roof, because the thatched roof has the lowest U value and the highest amount of energy saved per year. Okay, so we've got a saving energy per year of 205 units as opposed to 195, 200, and 188. So pretty straightforward if you can read the data there. If you understand the term U value, that makes it very easy, but then you would understand that the most efficient is the one that saves the most energy, and that's the link which makes this a higher tier question. Calculate the payback time for the recycled newspaper in years. Okay, so payback time is the time that it takes for a product to pay for itself. So you can see here the saving for the recycled newspaper is £200 per year, or 200 units per year. If the cost is £780, then you can see that the payback time will be 780 divided by 200. It's paid for itself in 3.9 years, so, or nearly 4 years. So it's very simple to do this calculation, but because you've got to pull ideas together from the table, this makes this a higher tier question. The payback time, as long as you can understand exactly what it's asking you, is very simple to do. Okay, so finally, suggest a U value for mineral wool and use the data in the table to explain your answer. So the U value for mineral wool is going to be somewhere between the U values for newspaper and sheep's wool, because if you look at the saving in energy per year is 195, which is between the saving for recycled newspaper and sheep's wool. So any value between 0.18 and 0.15 is going to be the best. Well, that really leaves 0.16 or 0.17, as long as we're keeping our answer to the same resolution. But the key thing here is this, is that I've chosen 0.16 because the saving energy per year for mineral wool is between those two, but closer to that for newspaper. So, so I've hedged my bets and I've put it there. So, so the U value will be proportionally between the two U values that we've shown there. Now, the last thing here is this, is that you can calculate that using ratios. Now, ratios is not something you have to use here, but it's something that's very useful to use. And if you understand how to use a ratio, this gives us a very, very accurate way of calculating something like this. So you can see that to calculate the U value using ratios, I found the difference between the U value for mineral wool and sheep's and recycled newspaper, the difference between the U value of of newspaper and sheep's wool, so that is 5 divided by 12, and that will be the same as the ratio of the U values. So if you can find the numbers that I've shown just there and see where they've come from, and then I've rearranged my equation to make U the subject. In fact, I've made minus U the subject. And I've got a value of minus 0.16, but if minus U is minus 0.16, then U is 0.16, as we've predicted just there, and that's correct to two significant figures. The exact answer using those values is 0.1625, but it's been rounded. And of course, keeping to two significant figures is sensible because that's the values that are quoted in the data. All right, now that is a higher tier question, and really something that hopefully, if you're higher tier, you'll be able to get a grasp of at least the payback time calculation. If you're able to use the ratio, brilliant. Those math skills will help you a lot in chemistry, physics, and biology. But if not, don't worry too much. Right, so just evaluating our outcomes. Hopefully we've talked about insulators and how we prevent thermal energy transfer, and we can also calculate the payback time for a range of different energy saving and insulation options. Finally, there are some exam questions for you to try. 3 exam questions. Shouldn't take you more than about 13 to 15 minutes to complete these. I'd like you to download those, have a go at answering them. Then you can either write by hand onto the questions and then take a photograph and resubmit that, or you can download a copy and type directly onto the document. But you can see that it will cover everything that we've spoken about in this lesson. Okay, good luck, and see you next time.